In the present lecture, we shall introduce a very important family of distributions called the exponential family of distributions. First, we shall discuss the one parameter exponential family of distributions, and then we extend our idea to the case of multiparameter exponential family. In both the cases, the support of the distribution must be independent of the parameter, and the parameter space is an open subset of real line. Some related examples are discussed in this connection. Finally, we shall discuss a result which is very useful in determining a complete sufficient statistic when the distribution is a member of an exponential family. In the present lecture, we shall discuss the concept of exponential families. Most of the parametric families that we have considered are members of what is called the exponential family of distributions. Let script f theta be the set of all f theta x such that theta belongs to script theta be a family of probability distributions, where the support set of all x such that f theta x greater than 0 is independent of theta and script theta is an open subinterval of real line. We say that script f theta is an one parameter exponential family if small f theta x can be expressed as small f theta x equals to e to the power q theta into tx plus u theta plus vx, where q theta and u theta are real valued functions of theta and tx and vx are real valued functions of x. If x1, x2 up to xn be IID with common PMF or PDF f theta x, then the joint PMF or PDF of x1, x2 up to xn is given by g theta x1, x2 up to xn equals to product over I from 1 to n f theta xi, which is equals to e to the power q theta into summation over I from 1 to n txi plus n into u theta plus summation over I from 1 to n sxi. Hence, g theta is again a one parameter exponential family. Let us consider some examples. Example 1. Let x follows normal with mean 0 and variance sigma square. Then the PDF of x is fx equals to 1 by sigma root 2 pi into e to the power minus x square by 2 sigma square, which is equals to e to the power minus log 2 pi sigma square whole divided by 2 minus x square by 2 sigma square, is a one parameter exponential family with q sigma square equals to minus 1 by 2 sigma square, tx equals to x square, u sigma square equals to minus log 2 pi sigma square whole divided by 2 and vx equals to 0. Example 2. Let x follows normal distribution with mean mu and variance 1. Then the PDF of x is fx equals to 1 by root 2 pi into e to the power minus half into x minus mu whole square, which can be written as e to the power minus log 2 pi whole divided by 2 minus x square by 2 minus mu square by 2 plus x into mu. If we set q mu equals to mu, tx equals to x, u mu equals to minus mu by 2 and vx equals to minus x square by 2 plus log 2 pi divided by 2, then we see that fx belongs to one parameter exponential family. Next, we consider third example. Suppose x follows Poisson with parameter lambda. Then the PMF of x is fx equals to e to the power minus lambda into lambda to the power x divided by x factorial, which can be written as e to the power minus lambda plus x into log lambda minus log x factorial. If we set q lambda equals to log lambda, tx equals to x, u lambda equals to minus lambda, and vx equals to minus log x factorial, then fx belongs to the one parameter exponential family. Next, we consider another example. Suppose x follows normal with mean theta and variance theta square where theta greater than 0. Then the PDF of x is given by f theta x equals to 1 by theta root 2 pi into e to the power minus half x minus theta whole square divided by theta square. Now, f theta x cannot be put in the form of a PDF belongs to the one parameter exponential family, and hence the family normal theta comma theta square is not a one parameter exponential family. We consider another example. Suppose x follows rectangular distribution with parameter 0 and theta. Then the PDF of x is given by f theta x equals to 1 by theta if 0 less than x less than theta equals to 0 otherwise. Since here the support of the distribution depends on theta, f theta x does not belongs to one parameter exponential family. It can be similarly shown that if x follows binomial distribution with parameters n and p, then the family of distributions of x is an exponential family. If x follows negative binomial with parameters r and p, then the family of distributions of x is an exponential family. If x follows Cauchy distribution with parameters theta and 1, then the family of distributions is not a one parameter exponential family. If x follows double exponential distribution with parameters 0 and theta, then the family of distributions is not a one parameter exponential family. Now, we would like to introduce the multi-parameter exponential families. Let script f theta equals to set of all f theta x such that theta belongs to script theta, where theta equals to theta 1, theta 2 up to theta k is a vector valued parameter, where script theta is an open set of r to the power k, and the support of the distribution is independent of theta 1, theta 2 up to theta k. The family script f theta is said to be a k parameter exponential family if f theta x can be expressed in the following form: f theta x equals to e to the power summation over I from 1 to k q I theta into t I x plus u theta plus vx, where q1, q2 up to qk and u are real valued functions of theta, and t1, t2 up to tk and s are real valued functions of x. Let us consider some examples. Example 1. Let x follows normal distribution with parameter mu and sigma square, where mu and sigma square are unknown. Now, the PDF of x is fx equals to 1 by sigma root 2 pi into e to the power minus 1 by 2 sigma square into x minus mu whole square, which is equals to 1 by sigma root 2 pi e to the power minus 1 by 2 sigma square into x square minus 2 mu x plus mu square, which is equals to e to the power minus x square by 2 sigma square plus mu into x divided by sigma square minus half into mu by sigma square plus log 2 pi sigma square. If we write q1 mu comma sigma square equals to minus 1 by 2 sigma square, comma q2 mu comma sigma square equals to mu by sigma square, comma capital T1x equals to x square, capital T2x equals to x, u mu comma sigma square equals to minus half mu square by sigma square plus log 2 pi sigma square, and Sx equals to 0, then Fx can be put in the form of a PDF belongs to the two-parameter exponential family. Next we consider another example. Suppose x follows beta distribution with parameters θ1 and θ2, where both θ1 and θ2 are unknown. The PDF of x is given by fx equals to gamma θ1 into gamma θ2 whole divided by gamma of θ1 plus θ2 into x to the power θ1 minus 1 into 1 minus x to the power θ2 minus 1, if 0 less than x less than 1 equals to 0 otherwise. Now fx can be put in the following form. Fx equals to gamma θ1 into gamma θ2 divided by gamma θ1 plus θ2 into e to the power θ1 minus 1 into log x plus θ2 minus 1 into log 1 minus x into I 0 less than x less than 1, where I bracket capital A is the indicator function for the set A. If we write capital Q1 θ1 comma θ2 is equals to θ1 minus 1, capital Q2 θ1 comma θ2 equals to θ2 minus 1, capital T1x equals to log x, capital T2x equals to log 1 minus x, u θ1 comma θ2 equals to gamma θ1 into gamma θ2 divided by gamma θ1 plus θ2, and Vx equals to I 0 less than x less than 1, then Fx can be put in the form of a PDF belongs to the two-parameter exponential family. Next we consider another example. Suppose x follows rectangular distribution with parameters θ1 and θ2. Then the PDF of x is given by fx equals to 1 by θ2 minus θ1 if θ1 less than x less than θ2 equals to 0 otherwise. Since the support of the distribution depends on θ1 and θ2, fx does not belong to two-parameter exponential family. Let us consider another example. Let x be a random variable which follows exponential distribution with parameters mu and sigma. Then the PDF of x is fx equals to 1 by sigma into e to the power minus x minus mu divided by sigma, where x greater than mu equals to 0 otherwise. Since the support of the distribution depends on the parameter mu, fx does not belong to the two-parameter exponential family. In all the above examples, we consider a single random variable x, but the concept of exponential family can also be extended to the joint distribution of p-dimensional random vectors. Consider the following examples. Suppose the joint distribution of x1 and x2 is bivariate normal with 5 parameters mu1, mu2, sigma1 square, sigma2 square and rho. Then the joint PDF of x1 and x2 belongs to the 5-parameter exponential family. We consider another example. Suppose x1, x2 up to xp jointly follows p-dimensional normal distribution with mean vector mu and dispersion matrix capital sigma. Here the joint distribution of x1, x2 up to xp belongs to the k-parameter exponential family, where k equals to p into p plus 3 whole divided by 2. Let us close our discussion with the following result. If the PMF or PDF of x belongs to the one-parameter exponential family, then the PMF or PDF of tx will also belong to the one-parameter exponential family. We consider a proof of the result only in discrete case. The PMF of x is given by f theta x equals to e to the power q theta into tx plus u theta plus vx. X belongs to script x, theta belongs to script theta, where q theta and u theta are real valued functions of theta only and tx and vx are real valued functions of x. Now the PMF of t is given by g theta t equals to summation over x such that tx equals to t f theta x, which is equals to e to the power minus u theta into summation over x such that tx equals to t e to the power q theta into tx plus vx, which is equals to e to the power u theta into e to the power q theta into t into summation over x such that tx equals to t e to the power vx. If we write a star t is equals to summation over x such that tx equals to t e to the power vx, then we get g theta t equals to e to the power q theta into t plus u theta plus h star t. Hence, g theta t also belongs to the one-parameter exponential family. The similar result holds in the case of k-parameter exponential family. In the present lecture, we have seen that most of the common distributions used in practice belong to the exponential family of distributions. For example, the binomial distribution, Poisson distribution, etc. But there are several distributions which do not belong to the exponential family. For example, the rectangular distribution or the Cauchy distribution. An interesting fact that we have observed in this lecture is that in case of normal distribution, normal theta, 1 distribution and normal 0, theta squared distribution belong to the exponential family, but normal theta comma theta squared distribution is not a member of the exponential family.